Hello, I'm Panxu from UCLA. I'm glad to present our recent work on sample-efficient policy gradient with recursive variance reduction. This is a joint work with Felicia and Chen, which has been published in ICLR 2020. In reinforcement learning, a policy pi is defined to be a probability function over the action space when the state S is given. Our goal is to learn a policy pi which maximizes the performance of the agent. The performance is defined as the expected cumulative reward. We assume the policy pi is parameterized by an unknown parameter theta. Then, to maximize the performance function, we can use gradient ascent to update the policy parameter. Since the performance function j is defined as the expected total reward, the gradient of the performance function is also an expectation over the data distribution derived from the policy and the MDP. To approximate this gradient, we usually sample n trajectories from the current policy and use the stochastic gradient to update the policy parameter. In traditional policy gradient methods, such as reinforce and GPOMDP, the stochastic gradient of the performance function is usually a Monte Carlo rollout from the current policy. However, the high variance of this stochastic approximation often restricts the performance and stability of the policy gradient methods in practice. In this work, we propose to update the policy parameter using a recursively defined semi-stochastic gradient, Vk. It is defined based on three terms. The first term, Vk-1, is the semi-stochastic gradient used in the last iteration. The second term, G theta k, is the Monte Carlo estimator of the current policy. And the last term, G theta k-1, is the Monte Carlo estimator of the previous policy. The difference between Vk-1 and G theta k-1 is a control variate that reduces the variance of this stochastic approximation. Moreover, since data trajectories tau j are collected from the current policy theta k instead of theta k-1, then the third term in the definition of Vk is not unbiased when taking the expectation over the current policy. Therefore, we need to use importance sampling to correct this distribution mismatch. Here is the summary of our algorithm, which consists of two loops. In the outer loop, we sample n trajectories to obtain the initial gradient estimator V0, and n could be a large batch size to ensure the accuracy of the estimate. In the inner loop, we sample B trajectories and construct the semi-stochastic gradient estimator Vk, and here we renumber the index as Vt(s+1), where B is a very small batch size compared to N. This significantly reduces the total sample complexity. Then we use our recursively defined gradient estimator Vt(s+1) to update the policy parameter theta. We proved the convergence of our proposed algorithm and show that in order to achieve the epsilon accuracy, the sample complexity of SR-VRPG is in the order of 1 over epsilon to the power of 3 divided by 2. Here, we compare the sample complexity of our algorithm with some existing methods, GPOMDP and the reinforce of vanilla policy gradient methods. SVRPG is another variance-reduced policy gradient method which does not have the recursive structure used in this paper. It can be noted that SR-VRPG has the lowest sample complexity compared with all these methods. Due to the novel stepwise importance sampling techniques used in our paper, the sample complexity of SR-VRPG is independent of the episode length h, which is also a major improvement of this paper. We conducted experiments on couple, Monte-Carlo, and the pendulum to verify the performance of SR-VRPG. It can be seen from the results that SR-VRPG converges much faster than vanilla policy gradient methods. and also the variance-reduced one as VRPG. We also conducted a sensitivity study of our algorithm on the batch size parameter B, and we found that a moderate choice of batch size B often leads to the best performance, which aligns with our theory. Thank you for watching.